Hello, Calc BC students. This is Mr. Beck, and this is our first opportunity to talk to each other about the idea of what calculus is. And the idea behind calculus is measuring change. Now, the notes that we went through today, we talked about discussing small amounts of change, and the best way to do that is with the concept of a limit. Question we have for you is, what is a limit? When we talk about limits, what you guys first learned in pre-calculus was really how to find limits at certain points. And that's using this kind of notation right here. This is read as the limit as x approaches c of f of x equals L, meaning the limit of our function as we approach a certain x value is some number. Specifically for the function that I have up here, f of x equals 3x squared minus 1. F of 1 is going to be 3 times 1 squared minus 1, or 2. And a lot of you are like, great, we know that. We've been doing that ever since really pre-algebra, if not before that. And I agree with you, but the question I have for you is, why are you allowed to plug in 1? Why that direct substitution of 1 into our equation? The answer is something called continuity, and that's something we're going to be exploring throughout the entire chapter and then into the entire course, because continuity is a very, very deep basis for what we need in calculus. So we're allowed to directly substitute if we have a continuous function. And again, we're going to talk about that. But what happens if I have the function f of x equals 3x squared minus 1 times x minus 1 over x minus 1? And this gets to the heart of how do we find the limit of that function? How do we find f of 1? If we try to plug in f of 1, we get 0 divided by 0, which, by the way, is very bad notation. 0 divided by 0, but that concept of 0 divided by 0 ends up telling us that, okay, we are not allowed to do that, so this is undefined. And because it's undefined, we need to figure out, well, what is f of 1 approximately? What would happen if x is 1? And as we get into the heart of the matter, if x equals 1, a lot of people like to do this, which I think is very, very poor, only just from the standpoint of we can't really cancel that x minus 1 unless we know that x is not equal to 1. So if we do that, we could say that this is 3x squared minus 1, where x is not equal to 1. And then I'm okay with this kind of notation, because what this shows is we are considering what our limitations are by saying x is not equal to 1. Now, we're going to come up with a theorem later on that says, okay, if we can turn a function that we don't know about, and we can use another function which is very, very similar to that, we can explore what's going to happen. Now, what I'm going to have over here is this is the graph of that function. Let me go ahead and show you which one is being highlighted. This is the graph of this function, 3x squared minus 1 times x minus 1 all over x minus 1. What I'm doing here is saying what is f of 1, and if you notice, in this case I call it h, but h of 1 is undefined. In order for us to figure out what h of 1 is, what we need to say is what happens if we have h of 1.1. And we end up with this y value of 2.63, which kind of makes sense if we take a look at the graph. Let's zoom in just a little bit. If we say h of 1.1, that's going to be roughly 2.63, which is right up here. Now, a lot of you are saying, well, this looks like it should be h of 1 is 2, but we know that point is undefined. What's happening here is our goal, and this is really getting to the heart of the matter of what a limit is, our goal is to determine, can we get close enough to figure out what h of 1 should be, or going back to the other screen, what f of 1 should be? Can we do that? And we're first going to do that as you're talking about what's happening really, really close. Now, if I plug in h of 1.1, 2.63 is not really close to the y value of 2, which is what we're looking for. So I would argue that this is not close enough. Well, what is close enough for me to determine what that y value should be? So if I plug in 0 here, you'll find now I'm much, much closer to the x value of 1, which gives me significantly closer to the y value of 2. But 2.06, in my opinion, is not 2. I know I'm kind of a stickler, so I'm not in full agreement that this should be 2. Well, let's get closer by putting in 0.001. And you can see that the y value ends up getting closer as well. And what if I said, you know what, 6 thousandths is not close enough for me? Can I get closer? So we can just keep getting closer with the x value to come up with a y value that's close enough. This idea of close enough goes into what the heart of what the limit definition says. This epsilon, if we want to know a certain epsilon, and that epsilon represents, let me zoom in here, that epsilon represents that distance between the y value and the error that comes up with our approximation. In the example that I just showed you, the y value that we're looking for is 2, and initially I had 2.6, which I said, no, I don't agree with that, that's too high. Eventually we started getting it down to like 2.006. At some point we're going to say, all right, it's close enough that I believe that that's what the limit is going to be, meaning that's what the y value should be. So at some point, and that's our epsilon, at some point, whatever we consider is close enough, we are able to create an x value that's going to correspond with that. And that x value goes along with this delta, where the x value that I initially chose was 0.1, or that delta that I initially chose was 0.1, which I said, no, it's not close enough. So eventually I plugged in like 0.001 and so on and so forth. This is the heart of what the limit definition says, and this is why it's so powerful, because what it says is we can always say what is close enough for us. We can choose a certain x value that allows us to get close enough, which says that the distance between the x value and the number we're choosing is small enough to imply that that y value is going to be within the tolerance level of what we want. So that's what a limit is. Now, how do we apply it? Initially, when we talk about calculus, really all mathematics in my mind goes into a threefold approach. That threefold approach is a numerical, graphical, and algebraic. What we did initially at the top was we kind of took a look at some algebra, and obviously when we went to the test method over here, we said, oh, let's take a look at graph to see if we can figure out what's going on. Now, my goal right now with you is let's go ahead and figure out what is, or how we come up with our limit, and how we come up with our limit based off of first a numerical approach, which that numerical approach I was showing you over here as I was plugging in smaller and smaller values. That's really how we establish what the limit is. So I had taken this function f of x equals x over the square root of x plus 1 minus 1. One of the things that you should note is what happens when we try to figure out what f of 0 is. F of 0 ends up being 0 over 0. And once again, this is bad notation. We really shouldn't say it that way. So f of 0 does not exist. But knowing that it comes from a 0 over 0 mentality is going to tell us a lot more things in the future. So since f of 0 does not exist, our goal is to figure out what is the limit as x approaches 0 of f of x. And to do that, we're going to do this numerically. Now, over here, I plugged in smaller and smaller values close to 1. I could have easily gone on the other direction and said, what happens if I wanted to do 0.99999? And once again, the closer or the more nines I put in here, the closer x gets to 1, which means the closer that y gets to 2. So with the problem that I'm looking for up here, f of x equals x over the square root of x plus 1 minus 1. Let me turn off the other graph. So when I'm looking at this function right here, I want to know what the y value is, and we could see it graphically. We could see that the y value should be 2. Now, what is f of 0? Undefined, just like we said. But if I plug in numbers, for instance, if I correspond with what I have on the paper, if I plug in negative numbers, I apologize. So if I plug in like negative 0.1, I'm close, negative 0.01, 0.001. Basically, the x value gets closer and closer to 0. I want to know what the y value gets closer to, which you can see if we look at this progression. And let me kind of highlight this, and let's choose yellow. We can see this progression if we plug in numbers and we get closer and closer and closer to the x value of 0, the y value approaches 2. And so we end up saying the limit as x approaches 0 from the left side. So that negative right here, that negative tells me that I'm approaching from the left side of the x value. That limit ends up being 2. And then let's go to the right side. I'll do this in orange. So as x approaches 0 from the positive side, so x is getting closer and closer to 0, the y value that comes out of that gets closer and closer to 2. So 0, 2. Now, if both are true, then we can combine both of those statements So if both those are true, we can combine both of those statements into one and say the overall limit is as x approaches 0 of f of x equals 2. Our second problem is done very, very similarly. I'm not going to walk through the actual graph and talk through all the different components. But if I take a look at my function that I have here, I want to know what's the limit as x approaches 0. And the reason why I want to know what x is approaching 0 is because f of 0 ends up being 0 divided by 0, which once again, bad notation. But what that means is the limit does not exist. And because our limit does not exist, then we can figure out, well, what is it supposed to be? What does it get closer and closer to? So once again, I start as x is approaching 0. My apologies, I had the wrong tool out. So x is approaching 0 from the left. We could see that the y value, as x is approaching 0 from the left, the y value approaches 1. As x approaches 0 from the right, the y value also approaches 1. So once again, we can summarize each of the individual statements into the limit as x approaches 0 from both sides of f of x equals 1. Graphically, when we go to find our limit, we could say graphically it's really, really easy. What's the y value when x is 1? What's the y value? That's 3. And what I talked about in class today was tying it into, okay, graphically we can see that, but what about that third component algebraically? And to figure this out algebraically, what I've done is I've taken this function right here, factored it, and the reason why I want to factor it is because I want to know what it is that produces that 0 divided by 0. And that 0 divided by 0, in this case, comes from the factor x minus 1 and that factor x minus 1. So if we remove that factor of x minus 1, what we end up with is a function which looks very, very similar. And that function that looks similar ends up giving us a way or an avenue of approaching it by saying, okay, that limit is this limit. So the limit of the top ends up being the limit from the bottom, and now we can directly substitute to figure out what this is. And this is our threefold approach. Numerically, we could do this. Graphically, we could do this. And then algebraically, we can find a way of doing this. And that is going to be our exploration for the day. Can we come up with all three components? Choosing another different type of function, can we find the limit as x approaches 1 of this function? What you should see is color-coded, and that color-coded is really help you recognize why I did what I did. So in order for me to figure out the limit as x approaches 1, what I had to do was first establish, am I approaching 1 from the left or the right side? In this case, I'm choosing the right side. So if x is approaching 1 from the right side, I will be using this function right here, because that's when x is slightly bigger than 1. And then directly substitute and I get 1. As x approaches 1 from the left side, that means I'm going to be using this green function highlighted up here. So I'm going to replace f of x with the green function, which is 1. Piecewise functions are very, very important to us because the world ends up being much more, or analyzed much more in a piecewise function way, rather than strictly one function. So typically in math classes before calculus, we don't talk a whole lot about piecewise functions. Yeah, we have you graph different things, but they all seem very contrived. In reality, we want to know a lot more about what happens with piecewise functions, and we're going to have to keep those at the forefront of everything in class. Yes, we're going to work with our other functions, but we're going to emphasize those piecewise functions. What I did on the notes is I went a step further and said, okay, well, I want to know not just what happens when x equals 1, but I established this question of what happens when x approaches -1. As x approaches -1, we end up, and we can see this graphically, as x approaches -1, from the left side, x is approaching -1 and the y value approaches -1. From the right side, as x approaches -1, the y value approaches 1. And for this reason, the limit does not exist. This is considered a jump discontinuity. So this is a jump discontinuity. And that jump discontinuity occurs when we approach two different y values. The next question I asked everybody is, for what values of this function is f of x undefined? And it's pretty clear that we came up with the two y values of x equals 2 and x equals -2 pretty quickly. If x equals 2, then we end up with a hole in the function. And the hole in the function means that we're going to have a limit. Now that hole in the function occurs mainly because we have the 0 divided by 0. Where on the flip side, if we have x is approaching -2, then if we plug in -2, we can see that it's not just a 0 over 0, we have a number over 0. That number over 0 ends up telling us that we're going to have a vertical asymptote on that graph. So if we have a vertical asymptote, what that does is that causes us to say we increase or decrease without bound. So increase or decrease without bound. And because we increase or decrease without bound, therefore we end up having no limit. If we just have a hole, we have a limit. And algebraically, what we could do is we could take this function, go ahead and factor it. So x plus 2, x minus 2, go ahead and factor it. And we can see what factors end up reducing. And when I say reducing, we end up removing those factors in order for us to find the limit. And graphically, we know that that's going to look like a vertical asymptote of x equals -2, horizontal asymptote of y equals 0. We know it's from pre-calculus. And we can see the increasing and decreasing without bound based off of the vertical asymptote. Now, we do have a hole here as well. And going back to that hole comes from the limit. In this case, the limit ends up being 1/4. I don't think I wrote that down on the set of notes, but this ends up being 1/4. And we can see that right here, the limit as x approaches 2 of f of x ends up being 1 over 2 plus 2, or 1/4. Here, if I want to know the x value where sine of 1 over x is undefined, well, sine of x is actually continuous everywhere. So sine of x is continuous, which means our only discontinuity is going to come from what's inside that sine function. Let me go ahead and highlight it rather than circle that. So when x equals 0, we end up with a discontinuity. Let's go ahead and take a look at our Desmos activity here and say, not that function, but what happens if we take sine of 1 over x? We end up with something that looks like this. Now, since it looks like this, let's try to zoom in to see, what this function looks like closer and closer. And what you should be able to tell is if I zoom in closer, it's not really helping me. So let's take a point. So let's actually come up and try to get closer and closer to 0. And you should see your screen freaking out a little bit because what's happening is this oscillation occurs faster and faster and faster as x approaches 0. So we're not able to accurately determine what that limit's going to be either graphically or algebraically because we don't really have an algebraic approach to this. Numerically, those numbers end up being so far all over the place that it doesn't seem worth it. So the limit we end up saying is undefined, and the reason why it's undefined is because of our consideration of oscillating behavior. Oscillating behavior. So to formally say it, our 3 reasons why a limit doesn't exist. We approach a different number from the left side and the right side. Once again, this is considered a jump discontinuity. F of x increases or decreases without bound. This occurs at asymptotes. And not just any asymptotes, it occurs at vertical asymptotes. Or f of x oscillates between 2 fixed values, what we saw in the third case. That third case ends up being not so oftenly talked about, but it's still an important thing to look at. So now that we've talked about how to find limits and how to establish when limits don't exist, the first and foremost thing is how do we find limits of continuous functions? And that would be direct substitution, and I mentioned that. Direct substitution only occurs because, and I'm going to highlight this because it's so important, if f of x is continuous, then we can directly substitute. If it's not continuous, then we have to find some other method. So all of these functions are continuous in the domain. And what I talked about in class is I want you to think through this in kind of a steady progression. First of all, let's identify what function do we have. and then know that that function is a continuous or not, and then work from there. So on problem A, very first thing I establish is what kind of function is this? This is a polynomial, and we should know the polynomials are continuous everywhere. Therefore, we can directly substitute. So we have continuity, so we can directly substitute, and we get the value of 66. On part B, let's take a look at this function that we have right here. We really don't need the parentheses, but I'm going to put them there anyway. Is this, or what kind of function is this? This is a rational function. Are rational functions continuous? No, this function is not continuous. Now, on a side note, this is continuous in its domain, which means we have to say, where do we have that continuity? It's everywhere but x equals -3, which then I go back and say, I don't care about -3, I care about 1/2, and since I only care about the 1/2, then I can directly substitute. So my train of thought is, what type of function is it? So let's identify that function. Does that function have continuity at the point or not? And if it does, then directly substitute. If not, then we have to do something alternate, and I'll explain that in just a moment. So part C, natural log function. Is the natural log function continuous? Yes, it is. It's continuous in its domain, and that domain is when the argument here is greater than 0. And since the argument is greater than 0, negative e to the 4th is part of that. Therefore, we can directly substitute and go. Hopefully, you're following along really well. Part D, what kind of function is this? This is a rational function. Rational functions are continuous in their domain. Therefore, we directly substitute. E, what kind of function is this? Well, this is really a composition of functions. And the composition of functions is, it's the product of a trig function and a polynomial, or in this case, it's the identity function. But this actually shows the one of the special properties of limits. The limit of the product we can turn into the product of the two limits. So this is something special that happens with limits, and that's why limits are such a powerful mentality. By breaking it up into its two separate limits, we can see exactly what's going on a little bit more clearly, and we end up with the answer of pi/4. F, the limit as x approaches 2 square root of 3 over 3 of the arcsecant of x. We have to establish, well, where is arcsecant? Undefined. Arcsecant is undefined when arccosine is 0. Talking through this just a little bit more. Basically, we're not approaching. Yeah, I actually said that wrong. Sorry, I went off my mental script. So let's just say, can we take the arcsecant of 2 square root of 3 over 3? Yes, we can. Can we take the arcsecant of a number bigger than 1? No, we can't. Can we take an arcsecant of a number smaller than 1? Nope. So really, we can just plug this in. This is a skill style problem, just to kind of bring back some of the different ideas. Which then we flowed into the theorem that I mentioned before, that what we did was we took the function that we had, and with that function that we had, we tried to reduce it to a function that's different. I'm going to highlight the difference by saying this is now a different function, but these two functions are equivalent everywhere except for the 1 point. And therefore, we have a theorem, and I wish I could go into that theorem, but I'm not going to. This theorem says that those limits are going to be equivalent. So it's something that we've done many, many times. Ways that we can algebraically or analytically try to come up with finding the limits. Direct substitution is the key if we have continuity. But if we get that 0 over 0, we can factor, we can rationalize, or simplify in some way. And the problems I have here kind of show all those different approaches. On 6, once again, the very first thing that we do is we plug in -2. The numerator goes to 0, the denominator goes to 0. Therefore, we're going to be able to find some analytical strategy. In this case, it was factoring. So we have the sum of cubes factored, and then we find the limit, and that limit ends up being 12. On example 7, we have a couple different approaches. We really could do the difference of, well, first of all, let's check the numerator will go to 0 and the denominator doesn't go to 0. Therefore, we have to find some analytical way. And when we do this, I ended up using Pascal's triangle to do this problem. Did you have to do Pascal's triangle? No. Could you have multiplied it out multiple times? Yes. Could you have used the difference of cubes? Yes. Any way that you do that, and honestly, I'm very, very happy with you doing any approach to the mathematics, then you simplify the expression down. Now, once again, this limit cannot be found immediately, but if we replace it with a function that is equivalent everywhere except for one point, and that is equivalent everywhere but x equals 0. Now we can establish the limit from that equivalent function to get 3. Problem number 8, not really any other approach that I can think of at the moment. Let's just go ahead and multiply those out. The numerator goes to 0, the denominator goes to 0, as shown over here. Numerator and denominator both go to 0. So we multiply it out, and that 0 over 0 ends up factoring out. We come up with our equivalent function, and then find the limit, which is 3. On example number 9, and this is going to be the beginning of a classic case, if we check, the numerator goes to 0, the denominator is 0. Therefore, we have to come up with another way. The strategy that we tend to use is the conjugate. We rationalize, in this case, we're rationalizing the numerator. We rationalize the numerator by multiplying by the conjugate of that numerator over itself. In this step right here, in this step, I simplified the numerator, so the numerator got simplified, but if you notice, that denominator stays multiplied out. And the reason why I do this is, what's the whole point of doing this strategy? Our goal is to figure out how we can remove that 0 divided by 0. To remove that 0 divided by 0, I really want to simplify the numerator because that 0 on the denominator has to be taken out, which I do, and I get 1 over the square root, or 2 square root of 2. On example 10, in this case, the numerator is not going to be simplified. It's the denominator that ends up being rationalized, and we rationalize the denominator by multiplying by the conjugate. And so this is multiplied out. Numerator, again, not simplified. And then when we reduce, that x minus 2 ends up factoring out with a negative, because the numerator is x minus 2, the denominator is 2 minus x. That simplifies to a negative 1. And then we plug in 2 and we get negative 6. On example 11, this is a special case where we're going to rationalize both the numerator and denominator, which if we try to do that, then we end up still having non-rational problems. But that's okay, because the aspect that we are multiplying by the conjugate, instead of a minus 1, we have a plus 1. Instead of minus x, we have a plus x. What that allows us to do is come up with a function which is now continuous at x equals 4, and we can do our direct substitution from there. The strategy for problem number 12, and this happens, and I'm alerted to this, when you see a fraction within that fraction. So multiple story fractions, what I did was I multiplied by the LCD of the multiple fractions. And by multiplying by the LCD, what that ended up doing, and this is really a trick that I don't like to say trick, but when we do that math, then what happens is your fractions within the fractions cancel, and then we have a little bit more easily simplifiable problem. There's still a little bit of work here, but that's okay. Now, I have a lot of students who like to say, well, Mr. Beck, I really like to just take these and combine them into one fraction and work with them then multiply by the reciprocal of the denominator. More power to you. As long as you're doing valid math, that's really what I care about. Do you have a valid approach from beginning to end? And in fact, that's how I grade it, and I was kind of showing you this. Do you have a valid approach to the problem? Can you simplify that valid approach? Can you come up with the answer? And then this point of my grading comes from, can you show all of your limit notation properly? We have limit here, we have limit here. We don't have the limit notation here, and that's because we are taking the limit by direct substitution. So that's how I grade those. Problem number 13, we're going to get used to seeing some of this notation a little bit more. This represents what's called delta x. Delta x is one variable. So let me go ahead and highlight this. This is the limit is delta x, meaning a change in x approaches 0. And this should kind of bring back some memories of pre-calc. But once again, this is a fraction within a fraction multiplied by the LCD over the LCD. And in doing so, I now have this expression, which is a simplified numerator. Then simplify that numerator even more. Create the function that exists everywhere, and that's when delta x is not 0. So these end up saying, you know, I want to say they're gone because they're not, but when delta x approaches 0, these are irrelevant. Therefore, we can then directly substitute. On 14, this is just one strategy out of many. If I multiply by cosine over cosine, cosine times tangent is sine. So cosine times tangent ends up giving us this value of sine. So I end up with cosine minus sine over sine minus cosine, which once again reduces to -1. And when I say reduces, as theta approaches pi over 4 is -1. Now this is a case, if you notice, I haven't been checking the 0 over 0, but the tangent of pi over 4 is 1. So this is 1 minus 1. This is square root of 2 over 2 minus square root of 2 over 2. So 1 minus 1 is 0, square root of 2 over 2 minus itself is 0, which is why we're taking this algebraic approach with the trigonometry. Now, I don't know if you remember from pre-calculus last year when we had all of those trig identities, those identities that we needed to say, okay, we know that these are equivalent, how do we come up with that? Well, in calculus now, we're using a lot of those mentalities from pre-calculus, what you did. Two special trig limits that we want to focus on is the sine of x over x. The sine of 0 is 0. And then, so sine of 0 over 0 ends up being what? And that's kind of our goal. And we can see by this graph, the sine of 0 over 0 will approach 1. Very, very special trig limit. This trig limit can be found using what we call the squeeze theorem. The idea behind the squeeze theorem, we use colors. Suppose I have a function, which I'm going to call f. I have another function that I'm going to call g. And with that in mind, I want to know what the limit of h is. Well, in order for me to figure out what the limit of h is, as long as f and g contain h everywhere along a set interval, then if the limit of the top one ends up being L, and let me see if I can show it to you. If the limit of the top function is L and the limit of the bottom function is also L, any function in between will also approach L at the same time. In this case, it looks like our limit's going to be 1 for f, our limit is 1 for g. Therefore, if h is in between, then that limit is 1 as well. It squeezes it. I do have a link on my Canvas page that takes you to the Khan Academy video that talks about the squeeze theorem. Very, very powerful and fun thing to do, but it's only going to be fun to do if you want to know more and more about it. So I actually have a proof of the squeeze theorem here, and I believe what's on Khan Academy talks to this in a pretty similar manner. This comes from our textbook. I'm not going to go into that proof as much as this is on the unit circle, and because that's on the unit circle, the sine of theta is opposite, or the tangent of theta is opposite over adjacent. So that's where we get tangent of theta. Then we're going to end up dividing by 2. Go to the Khan Academy video and talk through it. So I like to have the algebraic proof of the second one that's important, the 1 minus cosine x over x. Let's go ahead and show that graph just so that you have a little bit more buy-in that that's what the limit should be. That limit should be 0. Now this is an algebraic proof, and I do like the algebra. So this algebraic proof, I multiply by 1 plus cosine over 1 plus cosine. And in doing so, I end up with a trig identity that I can simplify. And once again, the product of the limits, I separated those limits. And in doing so, I can take them all individually, and I get 0. Now, these kind of problems are just working with that. In the first, in part A, I factored out the tangent, and sine divided by tangent is cosine. And so what you should see is I now have 3 times tangent over tangent times 1 minus cosine x over x. And so since this limit's 0, the overall limit's going to be 0. For part B, there was some manipulation that went on. If you notice, I turned secant into 1 over cosine, tangent into sine over cosine. I showed that if we multiply by cosine over cosine, we end up with the expression theta over sine of theta, which that limit's 1. And hopefully it makes sense that, and let's look at this. If the limit of that ratio is 1, and we reciprocate that ratio, the reciprocal of 1 is also 1. And for this one, we're going to see this in the other problem. If we negate that limit, the negative of 0 is our result, and the negative of 0 is still just 0. And now for part C, this is actually really the special case that we have. I did something a little bit different with this problem, where the sine of 4 theta over theta, we could look at this graphically, and we could say that 4 theta causes 4 revolutions to occur, so it's a lot faster. It's a lot faster of a function. I don't have this pulled up on Desmos, which is why I'm not showing you. But what I can do is I can manipulate this problem, and my manipulation is as follows. If I multiply by 4 over 4, this gives me the sine of 4 theta over 4 theta. Now, a lot of people will go, oh yeah, it makes sense, 4 theta over 4, sine of 4 theta over 4 theta, that should approach 1. But let's be a little bit more articulate about it. So I'm doing a substitution. I said if y is this value of 4 theta, then once theta goes to 0, 4 theta will also go to 0, which means y goes to 0. So now I could do this substitution that as y approaches 0, I now have sine of y over y. And as y approaches 0, sine of y over y, that's 1, which gives me the overall limit of 4. Last but not least, I am taking 3 different problems. What's happening is x approaches 1 from the left. What happens is x approaches 1 from the right. And can we have a concluding statement based on that? So if x approaches 1 from the left for this problem, that's how I get 0. I can plug in 1 there, 1 squared minus 1 is 0. From the right, 4 minus x, so 4 minus 1 is 3. Because those two limits are not the exact same number, the limit does not exist. If we substitute the limit as x approaches 1 from the left, right here, we'll get 1 plus 1, which is our 2. As x approaches 1 from the right, we're going to be using that. That's also 2. Now this is a special case that our limit from the left and right are both 2. F of 1 actually is 1 though. So we're seeing a case of, let me see if I can do this a little bit accurately. So this half is a parabola. F of 1 is 1, but this half is a line of x plus 1. Now this is a case where I don't care what f of 1 actually is if I'm trying to find the limit. This is f of 1. This tells us the limit as x approaches 1 right here. So that y value is the limit as x approaches 1. So there's a hole in the graph. This is like a displaced point. Our limit is going to follow what the functions do. Our limit does not follow what the point actually is. And we're going to talk about that more next time, that the limit in this case as x approaches 1 of f of x does not actually equal f of 1. And I'm going to give you a hint. This is how we prove continuity. Yay. And then for part C, we have something similar occurring, that since all the individual limits are -1, the overall limit is also -1. So we should say the limit as x approaches 1 of f of x does equal -1. This is the limit. Oh, that's what I have at the top. So x approaches 1 from the left, f of x. So because the limit of the left and the limit of the right is how we could say the overall limit. So those are my notes. Feel free to watch and rewatch and listen to my melodious voice over and over again. But if you don't want to do so, then I want you to have an amazing day.